so actually I will also cut time because we are far too late. If you look at the program, we are almost more than 30, almost 40 minutes too late. So I will actually skip, see my beautiful trailer on Brownian motion. And if somebody wants to see how Brownian motion looks, I have a beautiful movie. You can see it also on my homepage. But we have to cut time now. We have essentially no time. And first of all, I want to give you now another teaser. Why should you be interested in Brownian motion at all? First of all, you might not know so much about it or even nothing. On the other hand, you see at these names, all of these people have made a really salient contribution. Einstein, Lajavas, Molokhovsky, Ornstein, Uhlenbeck, Onsager, etc., Stratonovich. So it's a fact that these people actually have worked on this thing. You should maybe know something about it, or you have an own idea how to use Brownian motion in a different context. I will give you examples. Now, why you should do Brownian motion, because you should not be actually depressed, because all these smart minds already worked on it, because because the fact that so many smart people worked on it, it probably means that that is an important topic. That's what I wanted to say before. Okay, now let's see. And I start now with the Brownian motion. You can read it. Of course, it was invented by Robert Brown when he actually did those early experiments looking at how the grains of pollen move. And this story, you know, I go more in physics. It came an important thing. The theory of Brownian motion has a long history, but it started essentially with a person which is usually not so much well known. It's actually Bill Sutherland. Everybody knows about Einstein's contribution on Brownian motion of 2005 paper. And of course, Marian Smoluchowski had a much deeper understanding of Brownian motion, and Einstein said he understood Brownian motion, well, I actually didn't even know about the phenomenon in the first place. What is a bit interesting to say from a historical point of view, because at that time he was in Bern, and we had this group of always 4 people, which I will not give you the names because of time, and they studied actually all the papers of this famous, not so famous guy, but he should be famous, Bill Sutherland. And as a matter of fact, what we call the Einstein relation has been discovered and published quite a bit earlier than Einstein. But Einstein was a person, he was very convinced of himself, he essentially never gave credit to other people, which what they did before. And here I have the proof, you find all of this in my homepage. This is actually the text of the Sutherland paper where he balances the osmotic pressure force with the Stokes law force. And then, of course, having this relation, it follows immediately that, that relation here, that the diffusion coefficient is given here by the gas constant times temperature, so R over C is the Boltzmann constant, and even did the theory here for slip and stick boundary conditions to, so to speak, relate the Einstein relation. But you see, the Einstein relation is essentially already part here. You see it, all of this is written down in that paper by Sutherland, which was essentially 8 months published before even he submitted his work. Nowadays, just to advertise this, why Brownian motion is an important subject, I start with maybe the high energy physics and field theory. Of course, the path integral formulation is based on Wiener noise and things like that, and there's a field called stochastic synchronization. Even in finance and linguistics, we have a lot of Brownian motion theory, stochastic differential equation to explain the stock market development. Of course, chemical reaction, soft matter per se, biology now also all the time, and information science and geophysics. I will give you some example. And a little bit the problem is actually relativity and quantum relativity per se. I will actually relate to that because I did work in this also. And just another big problem we have as a physicist, usually we know the deterministic laws. For example, we have here a nonlinear resistant in contact with a thermal bath, with G of Q is a nonlinear resistant, and with capacitance C is a linear device. You know what the energy is essentially the charge squared over 2C. Q squared over 2c over kt is the equilibrium distribution, which has mean value 0. It's important that this is the correct stationary equilibrium distribution. If it would have a it is a Gaussian with vanishing mean. If it would have non-vanishing mean, you would get a finite voltage across the capacitance, and you could build an infinite series and get all kinds from Brownian motion. You would get for free any voltage you want. Of course, that cannot work, but it's a problem how to model now fluctuations, because you have the deterministic law. On the other hand, the probability theory tells you have the conservation of charge, and the probability is conserved. And when we have here a nonlinear Einstein relation, and what is important is here, if you have a state-dependent diffusion coefficient or transport coefficient, that's the second-order derivative, the Laplacian is sandwiched in between, in front of this transport coefficient and afterwards here, as you see. Now, how do you write down now, how do you treat now the fluctuations leading to this probability, to this overdamped Smoluchowski equation? Of course, most people would say you take the eta rule, you know, here's the Watt stuff, and you have here the eta rule with independent increment, which is, I will not go into the detail, but but if you do that and you don't add here with so-called this part in red, you will not get from this eta prescription to this Fokker-Planck equation. Most people say, okay, we use this Statonovich because that is considered normal using standard calculus, and this uses a midpoint rule, this uses a pre-point rule, and then you have to correct it with the green stuff here in order to get from this interpretation of stochastic calculus to this equation. I put forward, even as a PhD student, a different interpretation. It's called the Hänggi interpretation, or the transportation. Namely, I use the post point in the discretization of the Wiener increment between v of t plus delta t over minus v of t. You have to actually look at the post, and then you have to take the values at the post point and not at the pre-point and not at the midpoint. And when you get here 0, so you see, with this interpretation, you can use the deterministic law. And when you use this interpretation, and when you have no contradiction, because if you take any other contradiction like that one, if you would use this here with either eta or Statonovich, you would get the finite voltage across the capacitance. That would be terrible. And this is the other thing. And another people thought a long time of embedding quantum mechanics into Brownian motion. That's a little bit the story of abuse. I also worked on this. And I showed that this Nelson scheme of stochastic mechanics is essentially in several aspects not unique. For example, this diffusion coefficient h by 2 can be chosen arbitrary, and you can just correct this part with a constant. And most of all, as you know, if it would ever be a stochastic process, you must have, in quantum mechanics, for positive operators or symmetrized operators, you would have a positive value for correlation function. And you see here, this is a Hermitian construction of an observable at time t1 and time t2, and in order to get a real number, you take the symmetrization form. And these are positive operators, and then, of course, it's well known that the quantum correlation doesn't have to be positive at all. So it can never, quantum mechanics is never equivalent to any complex stochastic description, Markov or non-Markovian. So it's a no-go. And now I come to a little bit, I have no time to go into detail, but I will give you some aspects where problems still occur in Brownian motion theory. First of all, you are all familiar with Fick's law, or even the Fourier law in phonon transport, and usually the propagator is the Gaussian, and you start out with a sharp delta function, and you see at any later time t, the support of a Gaussian is on the infinite line. That is contradicting special relativity, that you have, so to speak, a finite probability at any distance away from the origin. That would mean that you have superluminal diffusion, so to speak, of a finite size particle, which is not possible because it would have to have infinite kinetic energy. Now the question is how to treat, for example, with non-equilibrium relaxation, which is consistent with special relativity. Many people put forward, especially the high energy community, something like this telegraphic equation here, which essentially is possible to get here no support outside the light cone, but it has fronts. But now fronts are unphysical. For a finite particle to move with the speed of light, it has an infinite energy. It cannot be the correct description, even though it's used in certain high energy communities. And so we have here a problem. And in addition, with such an equation, it has also been used in phonon transport for the Fourier law. But when you can show, you get a contradiction with the second law of thermodynamics. So actually, we put forward a path integral formulation, which I will not explain in detail. But you can actually do stochastic Langevin equation, but you have to go from position space into phase space, not into position and velocity, but relativistic momentum, and then you can overcome. And this leads to that old problem of inequilibrium. When you relax, what is the temperature in special relativity? In a wrap frame and in a co-moving, in a moving frame of constant, with an inertial constant velocity. Now, an interesting story is that not quite independent Planck and Einstein, the young Einstein and the Planck thought about that in 1907 or 8, and they said that the Lorentz transformation of temperature takes place where the moving body has a colder temperature. In 1963, there was a physicist Ott, but also an earlier paper by Sir Eddington claimed just the other way around. No, it should be hotter. And you see here the transformation law. And Van Kampen was already saying to me once early on when I met him, this must be nonsense anyhow. And he said the constant should stay, the temperature should not undergo a change, it should stay constant. And an interesting story, because Max von Laue worked on this too, and he wrote a letter to Einstein in around the mid-40s and saying that he uses now his result, that the temperature becomes cooler. And when Einstein said, "My dear friend Max, are you crazy? This cannot be right." And when Max wrote back, "Oh, well, I'm a bit surprised because you say so." In 2006, and I said, "Wait, I must then be wrong." But he, of course, didn't have the right answer either. And in the meantime, we did recently some in one-dimension computer simulation with binary collisions, and we could show, that's a longer story, that the temperature that made a lot of headline news in the American Physical Society, that the temperature stays, of course, constant and that does not have a Lorentz transformation, does not obey a Lorentz transformation law. Much more important, and this is still an open problem in field theory, is how to actually extend the beautiful theory of thermodynamics into general relativity and even into special relativity. And the problem is as follows. I give you only the aspects, namely in thermodynamics, you don't have local variables. You have to actually calculate the energy of a gas in a container. It's a global variable. And then, that's the first problem. And then, of course, how do you start? Because you don't have typically conserved tensor densities. The momentum energy tensor for a gas which is confined in a box does not transform in a Lorentz invariant way from a rest frame into a moving frame. So actually the whole problem is that you have to give up isochronicity. And you all have probably heard about the Lorentz contraction in special relativity of length, right? Sometimes even being taught. But you will never see, and nobody has ever seen a Lorentz contraction, you will never see one experimentally done. Because in contrast to things which happen at the local point, things which happen isochronous at different places in space will not be isochronous in a moving frame. And this is actually the problem, how to define our energy and total momentum. Anyhow, we actually put forward to overcome these problems a new insight. In order to have a consistent thermodynamics in special relativity and also in general relativity, you have to give up isochronicity, because always people try to add momentum at a constant time, like here at a constant time. We have here a hyperplane where also particle momenta would be added up at different places. This will give contradictions. And of course, we say basically the theory in our nature physics work here is that one has to go back to light cones, because this is the big problem. Distant stars from different distances need different times to go to a certain photographic plate. And all this has to be built in. It's too complicated. It will take 2 weeks to talk about it, but I'm very proud of this photographic thermodynamics, which is finally solving this problem of thermodynamics, at least in special relativity. I have not gone yet to general relativity. Now I give you 2 examples of Brownian motion-induced useful effects for mankind. One is the stochastic resonance, and let me see, and essentially, in a nutshell, it is the following. You have a very weak signal. My wife talks very softly and wants to tell me something. Said, what did you say? Of course, she says I have a hearing problem, but and how could I actually do something to get actually over that? Is namely in presence of noise. If we are actually in a party, in presence of noise, sometimes you feel that you understand better what somebody is saying in the silent voice. So you have an amplification, you have a weak signal, and you have presence of noise. And when you have a nonlinear system with a threshold system, and this is the effect of stochastic resonance, under certain conditions, not always, under certain conditions, you get actually an output signal which is amplified, okay. And you, essentially, this is you get a noise assisted synchronized hopping between, this is a model for this effect, where you have a bistable potential, and you tilt it to the left, and you tilt it to the right, so you have 2 times an escape. Here you take advantage that this barrier is lower. Here you take advantage the barrier is lower. So over a full cycle, you have 2 time points at half period where you have an advantage to hop. So we have here essentially a synchronization between a deterministic driving period where we tilt the bistable potential like that, and the random time scales the mean value of the escape time. And you can do. You see this even in simulation. You have a signal, and in absence of a signal, you have random hopping. And under the right dose of noise, if the dose of noise is appropriately right, you see here you get something like a stochastic synchronization phenomenon. Too much noise is bad, too little noise is bad. And this is how the whole field started, because people had 3 points of the ice ages, and Giorgio Parisi and other people made a diagram, calculated the power spectrum, and we found a peak of 100,000 years, and one knows that the giant ice ages are displaced by about 100,000 years. And when we think, there is, of course, always astronomical noise about, and also Earth noise, and the Milankovitch cycle has a time scale of the sun of about 100,000 years, but nowadays we don't have evidence that this is the correct explanation, because we have only 3 points. However, now talking about climate, which is now important, everybody talks about what's happening with the climate. There is occurrence of ice ages on a smaller time scale, namely of so-called Danskar-Oeschger events, which have a periodic time scale of 1,470 years. Say roughly 1,500 years. And we have here data over many years, over 100,000, 200,000 years from the Greenland Ice Sheet project. And now the question is, why do we have those small ice ages occurring on a time scale of 1,470? And this is actually based on a climate model, which goes back to Ramsdorff and other one, where actually stochastic resonance is at work, without going into more detail. And essentially, another important thing is that with deterministically driven stochastic systems has total different power spectrum. The Wiener-Khinchin theorem must be generalized to with time periodic driven systems using Floquet theory. And you see that you will never get in a symmetric system a response at 2 omega, only at 1 omega, 3 omega. So this has led to patterns to really distinguish between exact symmetry and not exact symmetry. Nowadays, we have all kinds of measures. We don't need periodic signals. We have also arbitrary signals. We use information measures like transinformation. And here we have 2 reviews on this effect. And now I give you a summary of this effect, that an amplification takes place for a certain amount of dose, here a maximum. If too much noise is bad, too little noise is bad. And when in this region you get more amplification, but what is more important than the maximum is the slope here, because that is the gain of amplification if you look at the slope. And as a matter of fact, this has several, I will skip that one. Nowadays we have, why is that an important effect? Because all you need is some kind of threshold system. Doesn't have to be a barrier, can be just a threshold, a neural threshold. You need to have a weak information type signal, and noise usually is ambient around for free. And when you get anomalous amplification properties, and this is essentially here, if you have a threshold, for example in hearing, you don't have enough spike in your hippocampus, you will not hear what you say, but if you have a little bit of noise, when you get more spikes, and the spikes are being transformed in your hippocampus to resolve the information. And this, of course, is taking place in the nicest example why this became now so famous in neurobiology. We have such threshold systems all around, and you can read, we have input currents as synapses processing along the axons, and then it goes into the hippocampus, and then you can see and hear and speak things, right? And just one important little example is this, where you can see this. You have here a cube, which is visual perfection. Now you can see this cube under this condition, until you focus on the base floor here, or you focus on the top floor here. You should see two different percepts of this cube. Now people did experiments where you can actually move this point from here to here in a certain frequency, and you see that in absence of this perturbation, that the power spectrum of those clicks, what you have the response changes a lot. And here you can actually relate that to stochastic resonance, let's say. Nowadays, this is a whole industry, namely it's called stochastic resonance therapy. You find it in all kinds of in doctors' labs, or also in what is called in chiropractical labs or physiotherapy labs. I mean, all sports people usually go before they go to the Olympic Games on such, for example, moving vibrating plates. Here is actually a beautiful experiment where you have young men and older men standing on a platform which is vibrating with mechanical noise. First of all, you adjust its sub-threshold, so the guy doesn't feel anything. You reduce the vibrations, he doesn't feel anything, and when you measure the sway, how everybody has a little bit shaken, he cannot stand totally still. And of course, in older people, you have more sway than in younger people, right? And now they add noise, and they find out that actually the stability of older people in walking improves to a certain measure, which is typical for young people. Can you imagine actually you stand on these vibrating plates, and when your motor control is much better. So actually there is something here around where actually giving the right dose of noise will improve, so to speak, the impairments of age-related stability motor control. And this is actually very useful. For nowadays we have also magic socks, and as I say, these plates are actually working all over. I had a student of mine which took once seldom antibiotics, and he could not stand anymore, could not really walk, and could not even drive bicycles. After 2 years in standing on such plates, he came back, and he walks now. So it's stochastic resonance from our physics people have an immediate effect over a time scale of 20 years. And here you see such older ladies standing on this plate, and which are typically shaking around, have a hard time walking. And now, if you stand, you have this effect. Of course, this is not real, but it goes in that direction. And nowadays, what is important, that we also for doctors, so brain surgeons, have special gloves which actually are vibrating either with mechanical noise or also works with electrical noise in order to really hand the operation with most precision. Okay, so now nowadays we have also a phenomenon quantum stochastic resonance. I just have enough in Nature Physics paper on this, but I will not go into this field which is presently active in the quantum stochastic in the quantum regime. Now I go to something which is has brought up by Mr. Smoluchowski, Marian von Smoluchowski. This is a picture from the Feynman lecture, so to speak, where you have a ratchet and a pole and a vane, and you can see that if the molecules hit from the right side, you can turn, and the other way around is more blocked. This is actually in the books of the Feynman lectures, but nowhere you see Smoluchowski. But I know from reading the Feynman stories that he was reading the Göttinger lectures of Smoluchowski of 1913. And Smoluchowski has written precisely this stuff. The Smoluchowski ratchet is part of his Göttinger lectures. And even here, earlier at the Physical Society meeting in Germany, he actually talks about in German about Zahnrad means ratchet and Sperrklinke means pole, and he describes that what he says, that you cannot drill a hole, it will not work, it will not be a system, but you cannot have a Maxwell demon. It's so interesting actually that the masters of that meeting in 1912 asked all kinds of tough questions after his talk. This is actually the description of 2013. And I translated that into English, and people asked him, is it not possible to use somehow the Maxwell demon, and if you would have enough intelligence openings and so on, and no friction to actually make a perpetuum mobile which violates the second law? And actually the answer of Smoluchowski was that this relates to intelligence, but intelligence goes beyond the physics. That's not the field of physics, intelligence. But and this is now interesting, I say this in this audience here, he had always a way out, kind of a loophole, because he continues his answers saying here, and I have to read it loud, it seemingly cannot seem excluded, sorry, it cannot seem excluded, that's important, that sentence to intrude, sorry, this is an important sentence, Marian Smoluchowski, 1912. Seemingly cannot seem excluded that the influence of intelligence, together with its mechanical operation, connected with work and dissipation of energy, lead to a possible compensation, and that takes place after all, and you don't get a steady motion. Huh? Nowadays, we know a lot about neuroscience, and we also know everything when you do get out work and heat, you have to actually also pay for it. So this goes back, I like that very much. I must say I like that very much. How much time do I have left? Where is my chairman here? Okay, so I will actually tell you now the modern language, how we get motion out, but we have to break symmetries. You are my chairman now. How much time is left for the coffee break? 5 or 10 minutes, okay. So let me advertise this, because we have to break symmetries, we have to break detailed balance, and when we're not anymore restricted to the second law, because the second law is a thermal equilibrium problem, which obeys a symmetry, the detailed balance, and if you break it, then things change. And of course here I give you the idea of a temperature or flashing ratchet. Assume you have a zigzag potential here, and you have particles located here. Now you heat it up as a function of time periodically to high temperature. So when the barrier energies at the high temperature are so small that you can neglect them, when you get here free Brownian motion, so to speak, now you see that this distance for this particle to diffuse over a short distance from here to here compared to the time it takes to travel from here to the long distance here will be much less likely. So if you do this periodically, you get essentially forward motion. Huh? And you can also do this with flashing. Instead of heating, you just switch off the potential. When there's no potential present, when you switch back the potential, which is actually used now in several experiments, also to flatten surfaces. And then, of course, you trap again. Okay, on, off, on is the same as low temperature, high temperature, low temperature. And then, of course, you get a motion, a directed motion to the right of impurities and things like that. And this works, but remember, switching on, switching off is non-equilibrium. You have to pay, it costs money to do this, and that's why you have to, the efficiency has nothing to do with the second law. Now, here you see, after you move right, you can also move upwards. like that with this mechanism, and this is an important parameter, how steep you can go upwards against the hill. And this is called the stopping force, and this is actually how one measures an important character of molecular motors, which take place all the time in your body right now as I speak. Okay, so this is essentially one thing. We have done here another pattern, namely want to move with this effect infected cells, which are usually bigger than healthy cells, using hydrodynamics and hydrodynamic interaction by pumping forth from back here. This is pores of about 10 million pores, which are asymmetric, as you see, on the square centimeters. And there are experiments, as I say, that's a length scale, there's a micrometer stuff of Brownian motion, and we have 10,000 pores, 10 million pores per centimeter squares. And this is our calculation. You can current reversal, you can pump really the particles depending on the diameter, either going left or right. And here is the experiment in nature, without going into details, where you can actually, switching off the pumping, you get no drift, switching on the pumping, you get the drift. And that's how you can separate the infected cells from the healthy cells without using chemical means. I have a little bit to say something in my last 2-3 minutes about quantum mechanics, namely quantum mechanics. To do this on the quantum mechanical level is quite complicated because you have to treat dissipation, and there's no phenomenological law on the system Hilbert space where you can treat dissipation. The problem with quantum mechanics is that you have always to go to the Hilbert space of the system, the Hilbert space of the path, which is usually infinite, and the interaction. And of course, so if you integrate out the path, you still have, of course, the fluctuating forces which are operators in the path Hilbert space. This is much more complicated than in classical, where the stochastic force is a classical force which is essentially acting then on your system variables. So that's why a lot of sense and nonsense is being published in quantum thermodynamics, in particular about heat. Because I have a theorem that heat in quantum mechanics cannot be defined, while work can be defined. But of course, heat is given as a difference of internal energy and work. And when you have the problem, heat depends on how you define internal energy and things like that. Okay, so this is another experiment where quantum ratchets have been done. And this is get new effects because of quantum tunneling. You see here, when you tilt the classical ratchet, you get always positive currents to the right in adiabatic limit. But if you tilt a quantum ratchet at low temperatures, now you get a battle between thermal activation, means high barrier paths, low barrier at low temperature, you have high barrier, there's a big arrangement factor. It's a battle, it's not good. But what helps you is not only from the gamma factor, not only the height, but also the thickness of the barrier. And if you tilt to the left, the thickness of the barriers are smaller as compared if you tilt to the right. And this gives you then a current reversal, which is solely rigorously induced by quantum tunneling. Okay, this I have no time. You can have also ratchets without dissipation. This relates to the field of K crystals, how to drive coherently systems and how to what to do in order to get directed current on such things here, like on this ring. And of course, there are modern directions where you treat active particles or Brownian motion under confinement. And then, of course, the big problem is that one has to take here hydrodynamics into account. Here you see you have a narrow position, here have a wide position, and the hydrodynamics around here is much more simple than the hydrodynamics here, where you have, so to speak, friction laws, but also hydrodynamic on scene type interaction and hydrodynamics wall interaction. That's something I do with the people in Shanghai and TDL Institute and the Shanghai Jittering University. This is a paper recently from Proceedings of National Academy, where the effect of hydrodynamics is up to 200%, as if you would neglect it. So coming to my end, I am in time? Of course not, but I want coffee. Yeah, that's okay, but I want coffee. We all want coffee. Okay.